Hydraulic machinery is commonly known for its exceptionally long operating life. However, there are conditions which may affect the as-built performance very rapidly, cutting down the life expectancy to only a few years. Abrasive erosion caused by suspended sediment in the water is the most serious of these unfavorable operating conditions. The early hydraulic engineers were confronted with this problem when the European Alpine region was developed. Today's hydroelectric installations, however, have to cope with much higher sand concentrations, particularly in Asia. Voith Siemens hydropower generation has therefore developed a comprehensive strategy to fight silt erosion. This strategy already incorporates the design of a hydraulic turbine. Modern numerical methods for flow computation are used to determine the velocity and pressure distribution in the flow passage. A knowledge of the flow field also allows the insertion of virtual sand grains to track their path past the turbine. To simulate the conditions of a particular project, Voith Siemens hydropower generation requests comprehensive information on sand characteristics, particle gradation, and so on. Inserting such a customized collective of sand particles into the numerical flow field yields reliable statistical information on the frequency and the location of particle impingement. Together with impact parameters such as velocity and impact angle, this information is used to determine the erosion attack, for instance, on the runner blade of a Francis turbine. Based on these results, the hydraulic engineer is able to modify the design in order to avoid local peaks of erosion. Together with a set of general design guidelines, the application of such advanced tools therefore enables Voith Siemens hydropower generation to optimize the design in order to reduce erosion. Nevertheless, in this way, it's clearly not possible to stop erosion completely. But modern material science provides numerous advanced techniques to significantly reduce wear on metallic surfaces. Voith Siemens hydropower generation, as a worldwide supplier of hydraulic equipment, is dedicated to a continuous investment in research and development. Today's basic research activities must comprise comprehensive material investigations. To do so, Voith Siemens hydropower generation is cooperating with renowned research facilities and institutions. For example, the Material Testing Institute, MPA, at the University of Stuttgart.
Modern technology provides a variety of different methods to cope with wear. However, the hydroabrasive wear, as it occurs in water turbines, is a very specific kind of wear and needs very careful qualification of materials.
The slurry pot test, for example. Cylindrical test bodies are fixed on a shaft which rotates in a clearly defined sand-water mixture. After a certain period, the mass loss of the test bodies characterize their abrasion resistance. These investigations have resulted in a distinct classification of coating techniques. The top end of this ranking, on the one hand, is clearly dominated by thermally sprayed hard coatings and by advanced polymer coatings based on polyurethane. Excellent abrasion resistance is obtained with the high-velocity oxygen fuel process. Amongst the polymer coatings, there is a clear classification with superior results for high-performance polyurethane materials, in contrast to these poor results of other systems.
The story report, however, shows some characteristics which make it difficult to transfer the results to real-scale hydraulic machines. This test rig provides flow conditions as close to real hydraulic conditions in the practice as reasonably possible.
Here, the shape of the test bodies corresponds to the geometry of an idealized hydrofoil. The test bodies are inserted into a converging test channel. There are geometry options for different blade curvatures. After insertion into the closed test loop, it's possible to expose the specimen to a clearly defined flow of sand-laden water. The high-velocity test rig is characterized by flow velocity up to 45 meters per second, flow with a stagnation point, pressure side and suction side owing to the curvature of the body, and accelerated flow resulting from the convergence of the test channel. The results essentially confirm the ranking which was found in the slurry pot test. Thermally sprayed hard coatings based on tungsten carbide have resulted in superior erosion resistance compared to the base material. Excellent results were also found with the high-performance polyurethane materials. Again, the tests confirmed significant differences within the class of polymer materials. A further criterion in the comparative assessment of materials is their cavitation resistance. Polyurethane samples have been exposed to cavitation in a high-pressure test channel of this type. A small hydrofoil produces a cloud of cavitation bubbles which implode on the walls of the test channel. High-grade polyurethane materials have proved to have excellent cavitation resistance compared to steel base materials. Thermal sprayed hard coatings can be tested for cavitation resistance with an ultrasonic test device such as this. The vibration of the test body is accompanied by a periodic pressure drop below the vapor pressure of water. The results show that high-grade HVOF coatings exhibit a cavitation resistance which is about 2 to 3 times higher than the resistance of the base material.
Laboratory investigations therefore have shown good prospects of various coating solutions. Reality, however, in many cases looks much different. Voith Hydro therefore has accompanied the research program with a number of experimental real-scale applications. Following, you will see a wrap-up of an in-situ application on a Kaplan turbine runner.
Here at the Inn power plant in Upper Bavaria, Voith turbines have been operating since 1936. Owing to sand erosion on these Kaplan blades, a comprehensive rehabilitation project is now on the way. The environmental conditions have to be closely controlled, mainly with regards to temperature, humidity and ventilation. A careful degreasing of the surfaces which are to be coated is essential for the success of the coating. To maintain long-term adhesion, a chemical surface pre-treatment has to be applied prior to the actual coating.
In this case, we use a polyurethane soft coating. Application can be done by spraying, by brushing, or even by troweling. In principle, therefore, it is a simple craftsman's process. However, every care has to be taken to ensure a proper surface preparation and a safe handling of the materials.
The application of a bonding agent as a second layer ensures the bond of the top coat to the base material. The final protective layer is applied by troweling. This is done using a multi-layer technique in order to build up a coating layer of about a 1.5 to 2 mm thickness. The final surface finish is achieved by using appropriate smoothing trowels. The application could also be realized by means of airless spraying. Experience with various prototypes has proved the good protective effect of soft coatings. The figure shows two Francis runners of a power plant after comparable operating. The soft coating has only slight local damage, which will not cause any further problems, owing to the excellent repairability of the material. Regarding the application process, soft coatings depend mainly on craftsmanship. HVOF sprayed hard coating, in contrast, requires a high level of control and sophisticated technology. Again, a careful surface preparation is essential for a good result. To achieve this, the workpiece is grit blasted to a specific roughness profile.
RZ36 ist gut.
Können wir so lassen. Starten.
The environmental conditions have to be closely controlled during the coating process. Noise, radiation and dust emission restrictions mean that the coating has to be applied in a suitable spray box. The distance and angle of the spray gun to the workpiece and the relative gun velocity must be kept within narrow limits. The coating of three-dimensionally curved surfaces, such as turbine blades, therefore requires the use of robot methods. In each path, the material deposition is only about 10 to 15 microns. To build up a layer of about 300 microns thick, the process must therefore be repeated about 25 times. Owing to this high level of control and sophistication, HVOF coatings have been used successfully for workshop applications on new machine parts. This is what an uncoated wicket gate looks like after 10 years of continuous operation in Africa, in comparison to a coated one after the same period of operation. Today, Voith Siemens hydropower generation is able to handle a full toolbox of erosion protection techniques. And these are soft turb, diaturb, tech turb. All these elements are covered by the Voith Siemens WISE protective system, which stands for Wear, Inert, Surface, Enhancement. This system offers a choice in selecting a remedy for most of the situations where sand abrasion is the reason for reduced life expectancy of hydraulic machines. So there's a good chance we can solve your specific abrasion problem. Voith Siemens Hydro Power Generation, the name for advanced technologies in hydraulic power generation. Contact us for the best available technology.